Introduction to semi-crystalline polymers. So first of all, let's start with the polymers. So polymers are long chain made of repeating monomer units, and I'm sure you know that semiconducting polymers conduct electricity when properly structured. And semi-crystalline polymer contain crystalline regions as well as amorphous regions. Here you can see in the diagram. So figure 1 and figure 2 shows the energy levels and density of states in crystalline and amorphous materials, whereas the figure 3 illustrates the basic organic photovoltaic device structure using P3SD PCM blend as an active layer. In crystalline region, order domains that facilitate charge transport, and while amorphous regions, disorder domains provide flexibility and solubility. So now we have the crystalline coherence length. So it is the distance over which atoms in a crystal remain perfectly ordered and in phase with each other. In figure 4 and figure 5, you can see that the technical electron microscopy image and schematic comparison of coherence length and crystallite size. So why CCl matters in organic semiconductors? So if we have the CCl longer, then it means we have fewer grain boundaries and defects, which improves the charge mobility. And in photovoltaics, longer coherence can help excitants move further before recombination. And it is studied using XRD or JXRD, technical electron microscopy, and AFM. So the texture refers to the preferred molecular orientation in thin films. Here we have edge-on and face-on orientations. So in edge-on orientations, it is generally common in OFETs, and the face-on orientation is generally common in solar cells. It is also studied using graphic incidence X-ray diffraction technique and AFM. And now we have density of states in organic semiconductors. So density of state refers to the number of available electronic states at each energy level that electrons can occupy. In organic semiconductors, material like P3SD and PCBM, the electrons in organic semiconductors. So the density of states refers to the number of available electronic states at each energy level that electrons can occupy. In organic semiconductors, materials like P3SD and PCBM are often disordered, and it also affects charge transport, recombination, and optics. Here in figure 7, you can see the density of states in organic semiconductors, and it can be studied using ultraviolet photoelectron spectroscopy and thermal admittance spectroscopy. So why it matters for morphology? Because it gives better ordering, and the molecular ordering and phase separation in a blend influence the density of states. So you can imagine it like a hotel. In crystalline materials, the hotel has well-defined floors with predictable rooms. But in disordered organics, the hotel is chaotic. Some floors are tilted, rooms overlap, and making it harder for guests, which is our electrons and holes, to find their way. And now we have the crystallinity. So what is crystallinity? So it refers to how ordered the molecular structure is within a material. If we have a high crystallinity, then the molecules are arranged in repeating ordered patterns, and low crystallinity means disordered amorphous arrangement. In figure 8, you can see the structure of amorphous versus crystalline molecular packing. So again, why it matters? Because it improves the charge mobility, it enhances optical properties, it stabilizes device performance. And in blends like P3SD PCBM, crystallinity affects domain purity and interfacial area, impacting efficiency. So it is also studied using X-ray diffraction technique, thermal transition by DSC, AFM, which is our atomic force microscopy, and UV-Vis. Now let's move on further to the topic cluster versus crystal structure. So clusters are small, locally ordered regions without long-range periodicity. It formed due to the incomplete crystallization and limited charge transport pathways. Whereas in crystals, we have highly ordered with long-range periodicity, and it also enables efficient charge transport due to better packing. Figure 9 illustrates the cluster versus crystal arrangement. And clusters have device relevance in OLEDs, sensors, early stage films, whereas crystals have OFETs, solar cells, and photodetectors. P3SD and PCBM blends contain both cluster and crystal domains, and the balance between these determines the efficiency of charge generation, transport, and extraction. So in the early stages of research of P3SD and PCBM blends, we have uncontrolled phase separation, which led to the poorly organized domains and inefficient charge transport. And this led to the suboptimal device performance in organic transport. However, as research progressed, significant breakthroughs were made in controlling the morphology of these blends, paving the way for improved performance in a variety of organic electronic devices. Now the key strategies that we have here is, first one is thermal annealing. So by carefully heating the blend, the polymer chains like P3ST are encouraged to crystallize, which improves their interchain order and charge mobility. It also helps to reduce domain size and improve phase separation, which allows us for better donor-acceptor interfaces, which is essential for efficient charge transfer. Here in figure 10 you can see the effect of thermal annealing. Before annealing, the substrate is this, and after annealing we have straight lines. And further we have solvent annealing. So in solvent annealing, the solvent vapors are used to swell the polymer film and allow molecular reorganization. The choice of solvent vapor is critical and depends on the solubility of P3ST and PCBM. So here are some commonly used solvent vapors: chloroform, which is good for both P3ST and PCBM; toluene, selectively for P3ST; and THF, selectively for PCBM. Next we have the additive engineering. Here we introduce specific additives to the phase separation of P3ST and PCBM, which influence the domain impurity and interface quality. Researchers commonly use high boiling point solvent additives that influence phase separation, crystallinity, and domain impurity. In figure 12, you can see the role of additive engineering in tuning P3ST and PCBM blend morphology. And there are many widely used additives like DIO, CN, and diphenyl ether. So the outcomes are larger and more uniform crystalline domains, which improves the charge carrier mobility. It also enhances donor-acceptor interfaces for more efficient excitant dissociation and charge transfer. It gives us greater phase purity, which minimizes recombination losses and maximizes device efficiency. So though these strategies, the blend morphologies has evolved into the uniform crystalline domains, improved interfaces, and high device efficiency, these breakthroughs have translated into improved OLEDs, OFETs, and other organic devices. So how it all started? So first of all, we have the breakthrough in organic solar cell. So in early 2000, the researcher discovered that how these two materials mix and their morphology was the key to efficiency. If we have the poor mixing, then the charge traps and we have low performance. But if the well-controlled phase separation, we have the efficient charge transport. This insight sparked intense research into microstructure control, crystallinity, phase domains, and interfaces. So one scientist saw how morphologic tuning could drastically improving solar cell performance. They asked, what if we apply the same principle to other organic devices like OLEDs, OFETs, and sensors? So in OLEDs, efficiency depends on how well electrons and holes recombine to emit light, and by controlling the domain size and purity in active layers, similar to P3ST PCBM solar cells. It also optimizes charge balance, emission uniformity, and device lifetime. And whereas the organic field effect transistors, which we have OFETs, rely on in plane charge mobility along the polymer chains, which is inspired by solar cell morphology control. And the sensors benefit from surface and domain engineering to increase interaction with analytes. They have morphology control, permeability, selectivity, response time. So the control of morphology at the nanoscale become a cross-cutting principle applied to OLEDs, OFETs, and sensors, fueling the rise of next generation organic electronics. So now we have reverse stream model. So reverse stream model, it gives a model that first, before the morphology, we have chaotic river, means we have disordered domains, blockages, and poor charge flow. But after morphology, we got a smooth stream. Like this one you can see in figure 13, which is the morphology evolution from disordered to streamlined charge, pathways in P3ST and PCBM blends. So as I told earlier, that initial devices had poor performance due to uncontrolled phase separation, but then the researchers analyzed that the morphology control was key to improving efficiency. And this metaphor illustrates the importance of controlled phase separation in enhancing device performance. Earlier we have single layer or bilayer, and the limitation we have that the poor excitant dissociation and charge extraction. But then we got the concept of bulk heterojunction. So it forms an impenetrating network of P3ST and PCBM, and this architecture provides a better interface area and continuous pathways for transport. Here figure 14 illustrates the evolution of device architecture from bilayer to bulk heterojunction concept. So at last, to conclude, morphology governs the efficiency of P3ST PCBM based devices, and features like coherence length, texture, density of states, and crystallinity are essential. And also strategies like thermal annealing, solvent annealing, and additive engineering are the key tools for optimization. And so now these principles are now being applied across the spectrum of organic electronics. Thank you. So,